First of all, Ramadan Mubarak to everybody. I know it's, so I hope you enjoyed your vacation, and starting Ramadan was easy because it was weekend. So let me remind you, we from the beginning of this chapter we started looking at magnetic fields, and we said magnetic fields can be caused by either a permanent magnet or a current that is flowing through a wire. That we will see in next chapter. Okay, and we said the permanent magnets, they always have a north and a south pole. And if you bring the north pole and north pole of two magnets, they will repel each other. South and south will repel each other, but north and south will attract each other. We also use the same concept of magnetic field lines to indicate the direction, and usually magnetic field lines, they go from the north to the south pole. And we said that if you have a charge that is moving with a speed of v, and it's in a magnetic field, it will experience a force, a magnetic force. And we said the magnetic force is given by F is equal Q V crossed with B. Okay, so that means the magnitude of F is Q V B sine of the angle between them. Okay, so if this is the magnetic field vector B and this is the velocity vector V, the angle theta is the smallest angle that the two vectors can make. And we said you can determine the direction of this using the right hand rule. And so you put the first vector V along your index finger, the second vector B along the middle finger, and the thumb will indicate the direction of the force. If it's a positive charge, if it's a negative charge, you have to reverse the direction. Okay. Then we started looking at particles that are moving in, due to a magnetic field, and we said if the magnetic field is perpendicular to the velocity, then the force will cause the object to move in a circular motion. And we said the circular motion can be, we can write, so this is Q V crossed with B. This is equal to the mass times the acceleration. And we said, so if the V and B are perpendicular, we can write this F is equal to Q VB. And this is a centripetal force. It's equal ma, and A is in this case V squared over R. Okay. And from this we can deduct the radius of the rotation of this circular motion. We can also determine the velocity V using this equation basically. Yeah? So, and we said the velocity V, if the particle is moving in circular motion, V is equal to the circumference, which is of the circle, which is 2 pi r divided by the period t, and hence we can get t is equal to 2 pi r over V. And so from here you get, so r is going to be mv over qb. Okay. And so the frequency of rotation, or how many circles or how many rotations per second, is given by 1 over t, and omega, which is the angular frequency, is 2 pi f. Okay. We also looked at the when an object is subjected to both magnetic and electric force. In that case, so if we have let's assume electric and magnetic force, so electric field and magnetic field B, then the force that the charge will experience is QE, the charge times the electric field vector, plus QV crossed with B. Okay, and we said many devices operate on this principle, and one of them is the velocity selector. For the velocity selector, the force is equal to 0, and in that case we have QE is equal QVB. The magnitudes. Okay. Also, the cyclotron is another device that operates on the mass spectrometer and the cyclotron and so on. So you can use these simple equations to describe to describe the motion of charged particle in the presence of electric and magnetic fields. Last time we stopped at what happens. We said when a current is flowing through a wire, the current is made out of charges. So let's assume it's positive charges moving in the direction of the current. In reality, it's really negative charges moving in the opposite direction. So each of these charges is going to be subjected to a force, okay? And so the whole wire will experience a force that is given by the equation F is equal I L. L is the length vector, which has the length of the wire and points in the direction of the current, crossed with the magnetic field vector B. So again, this is a cross product, and remember, we can write that the magnitude of this force vector is just ILB sine of the angle between the two vectors. Okay, so we said if the length of the wire or the wire is not perpendicular, like in this case, the wire has the length vector has a parallel component and a perpendicular component to the magnetic field vector, we can just multiply the perpendicular component, L perpendicular times B times I, to determine the force. Same thing if we have a wire that has a zigzag shape, like in this case, we can try to determine what is the equivalent length, or what is the length of this wire in the perpendicular direction of the magnetic field vector. So this is 90 degrees here. So if we determine this length, we can use the equation that the force is equal I L crossed with B. I think this is where we stopped before the vacation. Okay, so now let's go to the next part, and let me go to the presentation mode for that. Okay, so let's go to the next concept. Assume we have a wire that is not a straight wire, so you can see this wire is has some curves, and it's in a magnetic field. And let's assume also the magnetic field is not necessarily uniform. It can be a non-uniform magnetic field. Okay, so and we want to determine what is the force on this wire. So the way we can do it, we can break this wire into small elements, ds, and determine what is the force on each of these small element, ds's, okay, because at that location we know what is the magnetic field strength and direction, and so we can determine the force on that small element, the force on the next small element, and so on, and then we can sum all of these forces. Remember, if we make the summation, the increment very small, ds very small, the summation becomes an integration. So this is what we can do. So here we can take an element, ds, okay, and we can determine the differential force that is acting on this element. It's I ds crossed with b. Okay, so this is the same. So we replaced the L vector by ds because now we have a small element. Okay, and we can do the summation. The total force on the wire is the sum of all of these forces. Okay, and the summation becomes an integration if ds is quite small. So this is the new equation. The total force on a wire is I. You can take I outside the integral because we assume the current is constant here. The integral from the initial position to the final position, ds crossed with b. Okay, so this integral sometimes is easy to do, and we'll see at least one example. All right, so let me see if you can get the direction here. What is the direction of the field? So here you have a current flowing to the right, and you see the force is in the positive z axis. Okay, what is the direction of the magnetic field vector? So use the right hand rule and tell me if it's plus y-axis minus y-axis, plus x-axis minus x-axis, or plus z-axis. Okay, so verify it, use the right-hand rule. Okay, so who says plus y-axis? 1. Okay, who says minus y-axis? Minus y-axis. Okay, plus x-axis. جماعة يعني you're still in the mode of vacation. Or minus x-axis plus z-axis. What are the rest? يعني we have only one opinion. Okay, so let's repeat the question. Stay up with me, wake up يا جماعة. I know it's Ramadan, but so here you have a current and you have the magnetic force acting on the current. We want to determine what is the direction of the magnetic field. Okay, is it in the positive y-axis, negative y-axis, positive x-axis, negative x-axis, or the z-axis? Okay, so who says A again? Okay, so A, we have quite a large number. Who says B? All right. Okay, so let's try A. All right, so let's draw the vector like this. All right, now let's verify the right-hand rule. Okay, it's IL. So what is the L vector? This is the L vector here. This is the L vector. Okay, so it's ILB. So the first vector is L, so it's in this direction. Okay, if B is so here we want the force to be in the positive Z direction. So let me see if I can set it here. Okay, so this is the L vector. The force vector is coming out of the page. So what is the B vector? The B vector is pointing downwards. So it's the negative y-axis. واضح ولا should I repeat this? So because it's a little bit tricky, because you are given the direction of the thumb here, the direction of the thumb, and you are given the direction of the L vector, okay, and you are asked to determine the B vector. So here, this is the direction of the force, which is along the thumb, and so this is the L vector here. The B vector has to be pointing downwards. Okay, so this is right-hand rule. I don't know if the other way is easier. So we said it's so let's see. If you bring the L vector to the B vector, the L vector to the B vector, the thumb is pointed outward. So if you try the B vector up, you bring the L vector to the B vector, your force is going to be into the page. And you see here the force is in plus Z direction, so it's outside of the page. All right. Yeah, we have done this. Okay, so here is a problem. We have a wire that is bent into a semicircle of radius r and forms a closed circuit and carries a current I. So we have a current I flowing through the straight portion of the wire here, and also through the curved portion. The wire lies in the XY plane, and a uniform magnetic field is directed along the positive y-axis as shown in the figure. So this is the direction of the magnetic field vector. Find the magnitude and direction of the magnetic force acting on the straight portion of the wire and on the curved portion of the wire. So the straight portion is easy, because okay, the straight portion, the length in this case is 2r, so L is 2r, and this is the L vector here. So this is the L vector. So I can write for the straight portion F is equal I, the current is capital I, L crossed with B. Okay, so if you use the right hand rule, L is in the towards the right, and B is up. So the force is going to be outside of the page. So we can see that this is I, L, which is 2R. Let me replace L by 2R times B. And since the angle is 90 degrees, sine of 90 degrees is 1. And this is in the Z direction, so it's K direction. So this is the force on the straight portion of the wire. Let's do the force on the curved portion of the wire. So in this case, let's take an element ds, okay, and determine what is the force on this element ds. But so first of all, if we take the element ds at an angle theta here, notice that this same angle theta is this angle here, which is the angle between the vector ds and the magnetic field vector b. So let's write df is okay, so is the current I, and L is the S now crossed with B. Okay, since the S and B there is an angle between them which is theta, we can write that this is equal to, let's write the magnitude I ds times B times sine of the angle theta. Okay, and what direction is it? So let's see. If you bring the S vector to the B vector, you will find your thumb is pointing into the page. So it's in the minus K direction. So I can write minus K. What is ds? ds is the element of arc length here. And remember from physics 121, ds is equal r d theta. So I can write this is minus I r b sine theta d theta times k. Correct? Yes. Okay, so now let's try to, we're going to sum all of these elements. So we'll perform the integration. The total force F is going to be the integral of all of these elements, dFs. And so let's write this. So this is going to be minus I R B sine theta d theta times k. Okay. So what is the integral of sine theta? So this is going to be equal, and obviously the angle theta is going from 0 to pi. Pi. So the integral of sine is cosine theta. So we have minus minus becomes plus. So we have I R B cosine theta evaluated between 0 and pi. So this is going to be I R B cosine of pi minus cosine of 0 k. So I forgot the k here. Okay, cosine of pi is minus 1, and minus cosine of 0 is minus 1, so this will be minus 2 I R B K. So this is the force on the circular path of this wire. So this is, let's see, call this with F1, and this is F2. Okay, so here is an illustration of, in this case, how we can perform an integral. So we were able to make a change of variable of ds is equal r d theta and perform the integral. Obviously, you can sum of the two forces if you want to do the total force acting on this wire. So this is the same result. Okay, here is another example. Here we have a wire carrying a current I, 28 amps, and it has a linear mass density, lambda, So don't confuse it with the charge density. This is a linear mass density, so it's mass per unit length, 46.6 grams per meters. What is the magnitude and direction of the minimum magnetic field to balance the gravitational force on the wire? Okay, so obviously you can see, in order to balance the gravitational force, we have to have a magnetic force that is upward. So this is how. Okay, so in order we can use, like we did in the checkpoint, you have the L vector. So now the L vector is in this direction. This is the L vector here. Okay, and if you see if ILB, in order for the force to be in the upward direction, you can see that the magnetic field has to be outside the page in the Z direction. So this is the B direction, and you can check it. So you take the L vector, and the B vector, and the force is upward. Okay, so in this case, this is what is required. We need a magnetic field in the plus Z direction. So here we can, for the sum of the forces to be equal to 0, this will give me that the magnetic force is equal to the gravitational force. It's so I, L, B, and sine the angle theta, since the angle theta is 90 degrees, is going to be equal, sine of 90 is 1, ILB is equal to the gravitational force, which is mg. So we can get B is going to be mg, m divided by L, g divided by the current I. The current I is small case. The mass divided by the length is lambda. We already have the mass per unit length, so this is equal lambda mg. So this is the magnetic force that will balance the gravitational force. And if we replace the numbers, so this is a view of the same thing, but now it's a two-dimensional plot instead of three-dimensional plot. So again, the gravitational force pointing downward, magnetic force pointing upward. This is the L vector here. Okay, it's pointing in the same direction as the current, and you can see the magnetic field vector is pointing outside of the page. That's why it's represented by a dot. Okay, so you when you calculate B, you find that it's equal to 1.6 10 to the minus 2 Tesla. You have to convert grams to kilograms. It's 46.6 10 to the minus 3 kilograms per meter times G 9.8 divided by the current, which is 28 amps. You get the magnetic field strength. Okay, so these are all the equations we have done for this chapter. Any question so far? Any question about this chapter? It's all clear. So this chapter is an important chapter because we studied the effect of magnetic field on a moving charge, and we've seen that this is very important concept that is used in many devices still nowadays, such as the cyclotron, such as the mass spectrometer, velocity selector, and so on. Okay, so let's do some problem solving. Okay, and all right, so let me start the Kahoot. This is good to wake up your brain for the quiz. Okay, so let's see, start. So everybody enter the Kahoot, but I want you to work in groups of 2 or more. يلا شباب 1340158. Okay, so let me start the first problem. Everybody please log in because I use the Kahoot for attendance. Okay, so let's start. Okay, so 2 minutes for this one, simple problem, warm-up problem. So you want question A, eh? If you cannot read it, let me read it. An electron has a velocity v 2 10 to the power 6 I plus 3 10 to the power 6 j. It moves through a uniform magnetic field given by 0.03 I plus 0.15 j Tesla. Question A is find the force on the electron due to the magnetic field. And question B, repeat the calculation for a proton. So your answer A. So this is to verify that you can do vector cross product. This is very important for the coming part of this course. You have to be very good with the cross product. Ready? Huh? Huh? I'll give you more time. Please make sure you can you do this because this is the most basic question in this chapter. Raise your hand if you're ready. Raise your hand. Everybody should be able to do this one. Okay, I think probably more than 50% of the class is ready. Okay, so this is just basically doing the cross product. Okay, let me start the Kahoot. So choose between A, B, C, or D. Ready? Okay. 5 seconds. All right, so, okay, 1/3 of the class is correct, 13, and we have the rest, 11, 20 are incorrect, so 2/3. All right, so let's look at the, so I want to make sure that everybody knows how to do the, all right, okay, so this is the problem. So here we just do F is equal to Q V crossed with B. So you can either use the matrix method, or you can use, I can write this is minus E, V is 2 10 to the power 6 I plus 3 10 to the power 6 J crossed with B, which is 0.03 I, okay, minus 0.15 J. Okay, so here, so let me take minus E, leave it outside. Let me do the cross product first. Okay, so I crossed with I will give me 0, but I crossed with J gives me K, but we have a minus, so it's minus K. So 2 to the power 6 times 0.15, that's 0.3 10 to the power 6. We have a minus K. I crossed with J is K, and we have a minus, so it's minus K. Okay, now let's move to the second element, 3 10 to the power 6 J crossed with I. J crossed with I is minus K. J crossed with I is minus K. Okay, so it will be minus 3 times 0.3, so that's 0.09 10 to the power 6 K. And obviously J crossed with J will give me 0. Okay, so you can see I have a minus, so here I have minus E and times minus 0.39 K, so it's 0.39 times E times K, and this is the force. So if you look at the number here, you get 6.2 10 to the minus 14 newtons. Okay, obviously if the charge is positive, the only thing you replace minus E by E, the charge, so this is the charge of the proton, and it becomes minus, you get the opposite sign, minus 6.2 10 to the minus 14 newtons per coulomb. Next problem. All right, let's see the results. Okay, so many are correct here. All right, so this question, I'll give you 3 minutes. This is a little bit more challenging. So a proton moves through a uniform magnetic field given by B, 10I minus 20J plus 30K millitesla, so 10 minus 3 Tesla, at time t1. The proton has a velocity v, vxi plus vyj, they are not given, plus 2 kilometers per second, 2000 meters per second k. And the magnetic force on the proton is given, it's 4 10 minus 17 Newton I plus 2 10 minus 17 Newtons J. At that instant, what is the velocity Vx and velocity Vy? يلا يا جماعة, I want to see you writing, not speaking يعني. I want to see you writing and trying to solve this. You're not going to solve it by discussing, just discussion. So you have to write things down. Ready? If you're ready, raise your hand. Raise your hand if you're ready. Okay, so let's give more time. Ready? Raise your hand if you're ready. يلا يا جماعة. This is an easy problem. Let me give you a little bit more time. It's more difficult than the other one, but it's still easy. Okay, for the sake of time, so choose between A, B, C, or D. Okay, so I will go to the Kahoot. Five seconds. All right, well, even lower than the previous one. Seven students got it right. Okay. All right, so it's actually the same equation except we're solving now. Okay, so this is the problem, I guess. All right. So all right. So here we have the proton. So the charge is E. Okay, moves through uniform magnetic field given by 10 I minus 20 J plus 30 millitesla. All right, and we're given the velocity Vxi plus Vyj plus 2000 meter per second K, and we're given the magnetic force B, Fb, 4 10 minus 17 I plus 2 10 minus 17 J. All right, so we want to solve. The equation is the same equation. F is equal to Q V crossed with B. Okay, so instead of solving it the vector equation, let me use the matrix method in this problem. Okay, so the force F, we write it like this. So 4 10 minus 17 and 2 10 minus 17 J and 0 K. This is equal to the matrix I minus J K. Okay, And let's write the first vector, v. So this is vx, vy, and vz is 2000 meters per second. The second vector is the b. So this is 10 minus 3. So this is 10 to minus 2. Okay, and minus 20, 10 to minus 3. Okay, and 30, you know what, let me write it minus 2, 10 minus 2, and 3, 10 to minus 2. Okay, and we have to put E, so the charge of the proton. Okay, so this is I, J here. All right, so let's evaluate this matrix. So clearly, this one, the I component is this matrix. So 4, 10 to the minus 17, I is going to be 3, 10 to the minus 2 times Vy, okay, minus minus, so that will be plus, 2 times 2000, that's 4000, 10 to the minus 2. This is the first equation, huh? So this is the times E, yeah? So let's not forget the E. Okay, what is the second equation? The second equation is for the J component. So let's say 2, 10 to the minus 17 is going to be, so minus E times, so it's this matrix, it's this and this. Okay, so it's going to be minus E, so Vx times 3, 10 minus 2, so that's 3, 10 to the minus 2 Vx. Okay, and minus 2000 times 10 minus 2, so minus 2, 10 to the power 3, 2, minus 20. Okay, this is, so this is equation 1, equation 2, and you can directly solve for Vx and Vy. So you can see here you have everything. You can solve for Vy, and here you can solve for Vx. You can also do the other method like we did it before. So when you solve, you find that in this case Vy is 7 10 to the power 3 meters per second, and Vx is minus 3.5 10 to the power 3 meters per second. So you should be able to solve it either using the vector cross product or using the matrix method. Next problem. Right. 2 minutes for this one. An electric field of 1.5 kilovolts per meter and a perpendicular magnetic field of 0.4 Tesla act on a moving electron to produce no net force, zero force. What is the electron speed? 2 minutes. So here we have electric force and magnetic force acting on the electron, and they cancel each other. Sum of the forces is equal to 0. This is a one-step problem. Finished? Raise your hand if you're finished. Majority finished. Okay, so let's start the Kahoot. Choose between A, B, C, or D. 5 seconds. Okay, much better. So 19 correct and 14 incorrect. So this is the velocity selector. Okay, so this electron is subjected to a magnetic force. Let's assume it's going up, and electric force going down. So the sum of the forces is going to be equal to 0. We ignore the gravitational force. So the sum of the forces is equal to 0. That means QE plus QVB crossed with B is equal to 0. For this to be true, the magnitudes have to be equal. So QE is equal QVB. Q's will cancel, and you get V is equal E over B. So this is the velocity selector equation, and in this case you find V is equal to 3.75 10 to the power 3 meters per second. واضح, clear. Next problem. All right. Okay, so we have a streak of 3 correct answers. All right. We did a very similar problem before. So question B. So let me put it to 3 minutes for this one. So a particle moves along a circle in a region of uniform magnetic field B, 4 millitesla. The particle is either a proton or an electron. You must decide that. It experienced a magnetic force of magnitude 3.2 10 minus 15 newtons. What are the particle speed, radius of the circle, and the period of motion? So you're asked only for B, which is the radius of the circle. So we said, did we say 3 minutes? Yeah. We did the checkpoint for this one to verify whether it's an electron or proton. But now you're asked to solve for the values. Yalla Jama'ah, this is a very common problem that you can have in an exam. Okay, so choose between A, B, C, or D. This is okay. So I will start the Kahoot for question B, and this is the particle speed. Sorry, the radius of the circle. Five seconds. Okay, wow, 17 correct, huh? That's good. All right, so this is a problem, okay? So we know where is the force and the velocity vector. So this is the velocity vector here, V. The force is centripetal, okay? And the magnetic field vector is outside of the page. So now we use the right-hand rule. So we point the index finger in the direction of V. Okay, P is the second vector. The force is like this if it was a positive charge. Okay, so since the force is in the opposite direction, it's a negative charge. So the particle is an electron. So the particle is electron. Okay, so the next thing is we want to determine the particle speed. In any problem where I have circular motion, I always write this equation. F is equal to Q VB. It's equal to MA, which is MV squared over R. And I can solve. So first of all, the first question, it's asking for the particle speed. I have the charge of the electron. I have the magnetic field vector B. And I have the force F. So I can solve for V. So V is equal F over QB. This is the first question. The second question is what is the radius of the circle? From this equation here, you can solve for the radius. You can see that the radius is actually equal to QB over R is, sorry, let's see. So MV squared over R. R is MV over QB. MV over QB. The mass is the mass of the electron, which is 9.11 10 minus 31. The charge of the electron and the velocity vector, you have it from here. You can plug it and you have the magnetic field vector. You can find R. What is the period of motion? So for the period of motion, I always remember that the velocity is the circumference 2 pi R divided by the period t. So I can get t is 2 pi r divided by v. So since I have r and v, I can solve for it, okay? And also we have an equation. So if we replace this here, 2 pi mv over qb, and the v's will cancel, so it's going to be 2 pi m, the mass of the electron, divided by qb. So you can see that all of these equations are coming from this basic equation. So yes. Omega is 2 pi f. لا البيريد is something والأوميجا شوف البيريد الF, the frequency of is the number of terms is 1 over t. Omega is 2 pi f, which is 2 pi over t. Omega is the angular speed or angular frequency, you can say it. How many radians per second? The frequency is how many rotations per second. The period is how long it takes for a full rotation. So if you remember that this relationship, okay, if you solve for t, you can get the frequency, you can get omega, and so on. Okay, so I think we have time now only for the quiz.